So with a MOSFET instead of a BJT, this is going to be the circuit. So you have a basic common source stage. Right? Instead of common emitter, because now we have the source between the input and output. Your AC signal and bias circuit are applied to the gate, so this is VGS naught. And Vin at the drain side, we have used a resistor to convert the current from the drain into a voltage, and this is your V out, right? The only difference here is in AC and DC analysis, where you use the quadratic equations to figure out the bias point parameters, including the drain current, right? So this is the basic common source stage. Of course, you can have a resistor in the source, and it gives you the same benefits that we mentioned for the common emitter stage. In that case, you have a common source This is going to be your common source circuit with source degeneration. I'm going to analyze this because this is a little bit more complex than the basic stage, but once we are done, we can just set RS to 0 and apply it to the common source stage without a source degeneration. Right? Same thing as we did here. So in here, for a common emitter stage with emitter degeneration, if I analyze that at the very beginning and just set RE to 0, you would get the results that you had here. You know, they should basically be the same. If you set RE to 0, you're back to that circuit, and you can show it to yourself that it would be the case. Common source stage is going to be very similar. You know, I'm going to solve the circuit that is a bit more complicated with the source degeneration already there, but you can set RS to 0 and get the basic common source stage. So in this case, what I have is a small signal model that looks like this. So for a MOSFET, this is the small signal model. So GM VGS, and of course VGS is the small signal VGS now. I attached the rest of the components to this, RS, RD, V out, and in the input I only have V in. Okay? So this is the small signal equivalent circuit for the circuit to the left. Again, you know, re-emphasizing this, the device is in its active region. I've done the DC analysis. I've figured out the drain current, which is the important parameter here, right? And I've calculated GM based on that. Remember that, you know, for example, you can calculate GM from this expression. But there were 3 equivalent expressions that you could use, right? So I've calculated GM, and now I can build the small signal equivalent circuit to the right. I want to solve this, right? So I want to figure out input resistance here, output resistance here, and of course the voltage gain, the ratio of V out to V in. Okay, so let's start with voltage gain. I look at this circuit and I see that V out is the voltage drop across this resistor. The current through it is the current here, so V out is GM VGS RD. And similar to what we had for a BJT, I noticed that the current is flowing from ground up, so the voltage at V out will be more negative than ground. So this is minus GM VGS RD. Similar to what we had for a BJT circuit, common emitter stage. Now, I want to find the relationship between V out and V in. I have a relationship between VGS and V out here. So I would like to find next a relationship between VGS and V in. Well, I look at my circuit. A KVL here should give me that relationship. So I write it. So V in is VGS, the voltage drop across that open circuit, plus the voltage drop across this resistor. So the voltage drop across the source resistor is basically the current through it times the resistance. The current is this current plus this current, but I have an open circuit on the left, so that current is 0. My life is easier because the current from the right side is a current source. It's just GM VGS. That's the current times RS. Okay? So that equation right away gives me a relationship between VGS and V in. No other new variables are introduced. So basically, I should be able to combine these two, eliminate VGS between them, and show that my voltage gain is minus GMRD over 1 plus GM RS. Now, if you want to look at the more common, more basic stage without RS, basically an RS of 0, set that RS to 0 in this equation, and you get just minus GMRD for the gain. Well, this I'm hoping is still fresh in your mind. This is very, very similar to what we had for a common emitter stage. Right? The gain was minus GMRC divided by 1 plus GMRE. Now I just changed the variable names and got the same result here for a MOSFET. Right? So a common source stage in terms of the gain value, it's going to be very similar to what you get from a BJT stage. Now, one thing that will happen is that for a given amount of current, so for a BJT, 1 milliamp of current gives you about 40 millisiemens of GM. For a MOSFET, your GM value typically is smaller. So for, let's say, a 1 milliamp of drain current at DC, maybe you get a GM of 5 millisiemens or 2 millisiemens or something like that. So normally under similar conditions, you get a smaller gain out of a MOSFET than what you can do with a BJT. Of course, you can go and, for example, make your MOSFET wider, play with all sorts of, tricks that put the VGS very close to V threshold, so your ratio over there is larger. All those things you can do. But in general, for devices of the same size and then same amount of current consumption, you get more gain out of a BJT. And again, another way of convincing yourself that's the case is to think about what is that GM telling you. The GM is telling you how fast the output current changes when you change the input base emitter or gate source voltage, right? And for a BJT, you have an exponential growth. For a MOSFET, you have a quadratic growth. So therefore, you should expect a larger GM for BJT under typical device dimensions and concentrations. Okay? So the gain value at the end is, or the gain equation is very, very similar to what we had for a BJT. Let's do the input resistance part next. So input resistance, again, formally, we need to remove all the independent sources, attach a test source, measure how much current is drawn from the test source. In this case, my input source is an ideal source V in. I'm just going to calculate how much current I in is drawn from the source by the circuit, and that gives me the input resistance. I don't really have to use a separate source, which is exactly the same as this. But here is the issue. If I look at this, I in is 0. Right? In that circuit, the gate is an open circuit. There is no current going into the gate, DC or AC. And therefore, you can see that this gives you an R in that is infinite. Well, that is nice, right? Remember, for a voltage amplifier, we wanted a very large input resistance. Well, there is really nothing larger than infinite. There is really nothing that draws less current than an open circuit. It's zero current. So with a MOSFET amplifier used in a common source configuration compared to common emitter, you lose some on the gain, but your input resistance is essentially infinite, right? So that part is very valuable in a lot of cases. Where do I need an infinite input resistance? Where does that help me a lot? Well, in a typical voltmeter, you're putting the probe of the voltmeter on a node in your circuit. You don't want the voltmeter to affect the operation of the circuit. So there should be no current going into the probe of the voltmeter. What do you use? You use the gate of a MOSFET at that point and take the voltage at that node and amplify it using a MOSFET instead of a BJT. If you use a BJT, you will draw some current. You will load the circuit. With a MOSFET, yes, you may not get as much gain, but the probe is not going to affect your circuit. Same thing with an oscilloscope probe, right? There's a lot of applications like that this infinite input resistance is very, very valuable, maybe more than the gain. Now, here is a drawback, or here is another thing that should creep in your mind right now. Well, this is a basic stage, but I remember from 5 seconds ago that I cannot use this circuit. I need biasing. So as soon as you add the biasing network around your amplifier, you mess up the whole thing, right? So your input resistance that was infinite is now going to have a contribution from your biasing resistors and all that. But maybe we can do something about it if you're careful. Ideally, but as a simple stage, as I show here, it looks perfect. Infinite input resistance for that guy. What about the output resistance? Well, output resistance requires me to draw the circuit again, and I cannot really use the same circuit that I used for gain and input resistance calculations. So I redraw the circuit. GM VGS here, VGS here. Input source is now removed. RS down here. RD down here. And now I'm attaching my test source to where I want to measure the output resistance. The goal is to find IY. Then the ratio of VY to IY will give me the output resistance. I notice that IY is split between these two currents, between the current that goes through RD and GM VGS. So I start writing equations. IY is the current that goes through RD is VY over the RD plus GM VGS. Okay, the first part is okay. The second part has a VGS in it that I need to relate to VY if I want to get rid of it, right? So how do I do that? Well, again, maybe I can write a KVL here. I can write a KVL there and say that 0 is equal to VGS plus this current times RS. That current is just the current from the right side. So it's GM VGS. That's the current times RS. And I go back to ground. So from here, you can show that VGS is 0. And this is the same discussion as we had for the BJT. So I'm not going to explain this anymore. And therefore, GM VGS is 0. Meaning that this current source is actually not conducting. It's not, the current of that current source doesn't depend on VY. Right? It's a dependent current source. It doesn't depend on VY. So from VY's point of view, the value is 0. And then therefore, I can show that R out, which is VY over VY, IY, is just RD. And again, this is similar to my common emitter stage, right? For a common emitter stage, the output resistance was RC, the collector current. In here, it is RD, right? In fact, I can see that the MOSFET circuits are actually easier to solve than the BJT circuits because, for example, when I look at the relationship between the drain and source and all that, the drain and source currents are always the same. In a BJT, you have a contribution from the base that is going to show up in the emitter circuit. For a MOSFET, it's just drain and source. They're always the same current. Therefore, my equations are usually a bit simpler. Now, if you are a little bit adventurous, what you can do is that you can go and have a look at this small signal model for a MOSFET and say, you know what, this looks like a BJT whose R pi is infinite, right? So what if I go back to my BJT calculations and I set R pi that is approaching infinity? So I have a gain of GMRD over 1 plus GMRS, R in of infinite, and R out of RD. Let's see what happens if I go back to my BJT calculations here and take R pi and set it or make it approach infinity. Well, it doesn't affect the gain because there's no R pi there. It doesn't affect R out because there's no R pi there. But for R in, I can see that it is R pi times 1 plus GMRE. And right away, if I set R pi to infinity, I get the equations for MOSFETs. My whole point here is that the MOSFET small signal analysis is actually easier than BJT small signal analysis. And for the other two circuits, two other common amplifier stages that I'm going to talk about, I'm going to stick with the BJT that is a little bit more complicated, but the MOSFET one is going to be very, very similar. You just replaced RC with RD, RE with RS, and if we have a gate resistor, RG and RB. So that's that. Now the other point I wanted to make here is that it doesn't matter for a BJT amplifier. It doesn't matter if you use NPN or PNP. Yes, the DC analysis will be different, but once you get to the AC analysis, once you get to the small signal performance, the small signal model of a PNP is exactly the same as the small signal model of a PNP and NPN. They are the same, right? So the directions of the currents, the polarities of the voltages, all of them are exactly the same for the small signal of a PNP and NPN. And therefore, once I do the analysis for the DC part and have my GM and pi values, once I get to the AC analysis, the small signal analysis, I wouldn't know the difference. If I show you a circuit, only the small signal circuit of an amplifier, you cannot tell from that if the transistor used was a PNP or NPN. It's the same, right? So I'm going to limit the, at least lecture time to N-type devices, NPN and MOSFET. The P-type devices will be exactly the same, right? You will have some samples for P-type amplifiers in your practice problems and assignments. So make sure that you practice with them, but keep in mind that in terms of small signal behavior, they're exactly the same. Another thing that we learned today was that, yes, the small signal analysis is, let's say, universal. Anytime that I tell you that, there's a small signal that is affecting a circuit, you can go and draw the small signal model and solve the small signal circuit. And you should do that for at least 20 to 30 problems. You need to have that much practice in order to feel comfortable with it. But from time to time, I show you a circuit that you can reduce to something that you've analyzed before, right? So in this case, this common emitter stage, we looked at it closely. We noticed that, everything after RB1 and RB2 and before RL, we analyzed before. We know what that component, what that portion in between does. It has an input resistance, output resistance as a gain. So instead of doing a full small signal analysis, I replaced that middle portion with the equivalent amplifier and attach the rest of it to it. Now I'm looking at AC conditions only, so the capacitors go away, the DC sources go away. But it saves me time if I can identify the stage and use those formulas that we have. So we call this an AC analysis, any AC circuit analysis. The only difference between an AC circuit and your small signal circuit is that I do not draw the small signal model for the transistors. I just keep the transistor there. I try to figure out if it is a circuit that I've seen before. And once I'm convinced, once I'm sure that this is the same as, the common emitter with an emitter degeneration or a common source with a grounded source or anything like that, once I'm convinced of that, I have a set of tables and formulas for those three basic stages that I can use. And I will give you that as on Canvas. You can go and refer to them, right? So if I can break down the circuit into, let's say, biasing and load and the core stage, you can do that. When can't you do that? Well, if I put a resistor between, let's say, drain and gate here, then you cannot break that circuit back into this. There is a connection between the input and output that is not through your MOSFET. In this circuit, it's only the MOSFET that is connecting the output to the input. If I put a resistor between the, let's say, gate and drain here, your input can leak to the output through that resistor, or your output can go back as feedback to the input, right? So this is not your basic circuit anymore. If I give you a circuit like that, if you see a circuit like that, you have to go and draw the small signal model and then solve it using a small signal model. But if I don't have anything like that, if I don't really create additional current leak path, from, let's say from output to input or from base to emitter or things like that, then you can go and use the formulas that you have with this stage for the input and output resistances as well as the voltage gains and solve your circuit a little bit more quickly. There's plenty of samples on the lecture slides for this. There's plenty of samples in your textbook on this, solved and as practice problems. And there are a couple of them on your assignment as well. So make sure you get a lot of practice. Start by solving 10, 15, 20 problems, at least that many, with full small signal analysis. Make sure that you're very, very comfortable with it, and then start solving them using this AC circuit method once you have that insight from the small signal analysis. The point to remember here is that even if you don't want to solve it using AC circuits, you know, if you you're unsure when you see the circuit, if it is really the common emitter that you saw before or not, or if it is really the common collector that you saw before or not. You can always, always, always go back to small signal analysis, draw the small signal model, and solve the circuit using that way. It may take a bit longer, but if you have the time, or if you're not sure that that's the right approach, the AC circuit is the right approach, feel free. Go and use the small signal model and do it. And if you have practice with 15, 20 problems on small signal analysis, you'll be fast. You'll be fast enough that you can solve that circuit on an exam date in time without really using the AC circuit simplifications. So that's that for this lecture today. Next lecture, I'm going to talk about the common base and common gate plus common drain and common collector stages. These are the other two stages that we can make with a basic amplifier stage. We just saw it at the very beginning that you only have these many possibilities. We talked about common emitter, that is the most common amplifier. Now the other two we cover in the next lecture video. Actually, I'm going to cover common collector mostly, and common base and common gate we just briefly touch. After that, the discussion will be about biasing of the transistors, and that will conclude our discussion on transistor amplifiers.